In the world of engineering and automation, understanding how open and closed-loop systems work is crucial. Control theory plays a significant role, from industrial processes to everyday devices, in ensuring efficient and reliable operations. In this video, we break down the concepts of open and closed-loop systems, exploring how they differ and how they function, with clear explanations and examples to help you grasp the fundamentals of control theory. If you're new to control theory or need a refresher, this video is perfect for you. Whether you're an apprentice, a student, an engineer, or simply interested in learning about this topic, our video offers an accessible explanation that anyone can understand. Have you ever wondered how engineers and scientists manage to control complex systems with accuracy and precision? Well, they achieve that by a field called control theory. However, we have found that at least 90% of the work we do in our various institutions is not new, but rather variations or different setups of solutions that are already solved. So all that is needed is an understanding of how the pieces are constructed and how they relate to each other is the only thing that matters, not how they work on their own. An example of this can be shown by positioning your phone so that it recognizes your face and unlocks. Not necessarily how the phone exchanges signals with your face to unlock the screen, what matters is how you hold it in front of you. Certainly, safety is a critical consideration in control theory, ensuring that controlled systems operate within secure and dependable boundaries. So, use guidelines to make sure you don't use the system more than it can handle or do. Open and closed loop falls under a field of study called control theory that focuses on understanding the behavior of systems and developing techniques to manipulate them to achieve desired outcomes. It involves analyzing the dynamics of a system, designing control algorithms, and implementing them. So now, let's first look at closed-loop system, also known as feedback control. To know how closed-loop systems work, we need to learn what feedback is, and how these systems use it to keep checking and changing the output to get the result we want. Closed-loop systems consist of three main components: the sensor, the controller, and the actuator. The sensor measures the system's input or output, providing feedback to the controller. The controller then processes this feedback and determines the optimal control action, which is sent to the actuator. The actuator adjusts the system's input to achieve the desired output. Once the actuator reacts, another loop feedback is sent to the controller. The controller accesses the information and then determines whether the actuator should retract. This is usually represented in a block diagram as reference input, controller, process, output, and feedback. One of the most common examples of closed-loop systems is temperature control. Imagine you want to keep your room at a comfortable temperature, say 25 degrees Celsius. You set the thermostat to that temperature, and the system goes into action. Now, the input sensor in the system and the thermostat monitors the current temperature. If it detects the temperature dropping below 25 degrees Celsius, it sends a signal to the controller. The controller analyzes this signal and activates the heating system. As a result, the room temperature starts to rise. Once the temperature reaches the desired level, the sensor detects it and sends a signal to the controller again. This time, the controller stops the heating system, maintaining the temperature at the desired level. This continuous monitoring and adjustment process ensures an optimal room temperature. Leave in the comment section an example of a closed-loop system you can imagine. Let's now see what an open-loop system looks like. In this self-explanatory block diagram, an open-loop system, also known as feed-forward control, is a type of control that works based on a fixed input, with no way of checking the results. Basically, once the input is given, the system does what it is supposed to do, without caring about any changes or problems along the way. To make this clearer, here are some everyday examples of open-loop systems. An electric hand dryer is a good example of an open-loop system, which is a common fixture in public restrooms. Most modern hand dryers use infrared sensors to detect presence. However, they lack feedback mechanism to prevent activation when it detects a dry hand, or to deactivate when it detects that moisture has completely dried. So, when you place your wet or dry hand under the dryer, the system activates. The input is your hand being detected by an infrared sensor, or pressing a switch button to typically adjust the drying time. The heating element then starts producing hot air, blown by the fan onto your hand, helping to evaporate moisture, regardless of whether your hand is wet or dry. The system operates for a predetermined duration, usually around 20 to 30 seconds, before automatically turning off. This is an open loop because it lacks any feedback mechanism to assess the actual drying progress. It doesn't measure the moisture level on the user's hands or adjust its operation based on real-time conditions. Instead, it follows a fixed time setting, irrespective of the effectiveness of the drying process. A vegetable blender is another example of an open-loop system because it runs without feedback. When the user starts the blender, it operates at a set speed or time until manually stopped. The consistency or texture of the blended vegetables doesn't change automatically during the blending process. Rather, any adjustments are made manually by the user to get the desired result. Immersion rod water heater and a bread toaster are common open-loop examples. Both open-loop and closed-loop systems have their advantages and applications. Open-loop systems are simple, low-cost, and allow for easy implementation. They work well when the output doesn't require adjustments based on changing conditions. In contrast, closed-loop systems provide accurate and adaptive control. They excel in situations where maintaining a certain desired condition or set point is critical, especially when dealing with changing environments or variables. Control theory is a vast subject with many intricacies, but grasping the fundamentals is essential. We encourage you to explore further and discover the role control theory plays in various aspects of our daily lives. If you found this video helpful, don't forget to give it a thumbs up and subscribe to our channel for more educational content. If you have any questions or suggestions for future videos, please let us know in the comments section below. Click the bell icon to receive notifications and stay updated.